Hi, everyone. Thank you for joining me today. I hope you had a good coffee. I haven't had coffee yet, so that's going to be my treat after this talk. Today, I want to talk to you about there's two schools of thought here. The Americans say it idempotency, which is the way I remember it the best, but the British have corrected me and said it's idempotency. So choose the one that you would like to say. So this talk really began when I was on the way home on a road trip with my husband. My husband and I are both developers, and so we get into some really nerdy conversations. And he works at Amazon. He's an architect at Amazon. And so working with the kind of scale that he does, like hundreds of thousands of transactions per second, we got to talking about what those requests look like and what they need to be, and how, if you're going to operate at the scale of Amazon, say on Prime Day in North America, you need to have idempotency built into your request. So we said, idempotency, that's the most important thing that you need to have. And as we kept talking about it, it's kind of funny because we talked to a lot of developers, and a lot of them say they've heard the word, they kind of know what it's about, but really, when you think about implementing it or what it actually means, or you try to explain it in the context of a request, it kind of gets a little murky. And so that's what I wanted to do today, is to make it extremely clear not only how to pronounce it, but what it actually means. So very quickly, the agenda we'll go over is item what. We'll actually get a definitive guide on what that word means. Then we'll talk about why idempotency it goes hand in hand with really good serverless architecture. And really, I use serverless in this example, but this can mean any distributed system, and serverless is distributed systems. Then we'll talk about safe retries, because this is a very important part of any distributed system that you might build. And finally, we'll see how you might achieve idempotency on your own through some resources, some tools that I've found, and some that actually encourage or have idempotency built in. So item what? So Alex has already asked, but raise your hand again. Who here has heard of the word idempotency? That's a good chunk. Who here can switch places with me and explain it to you? Oh, would you like to take over? Okay, that's fine. So idempotency is this magical word, but the really funny thing is idempotency is not a real word, at least not according to Merriam-Webster's dictionary. In fact, if you take a look in the dictionary and research it exactly the way that it's spelled, it doesn't exist. The real word is idempotent, and in it, they describe it as relating to or being a mathematical quantity which, when applied to itself under a given binary operation, equals itself. So very thorough, but very useless to me, especially if you don't know what it means. But in the great words of Kevin from The Office, why waste time, say a word when few word do trick? I like Random House Webster's definition better, which is unchanged when multiplied by itself. And that makes a lot of sense, because when you think about multiplication, that's where idempotency comes into play. When you multiply two things together, they always should equal the same thing every single time. And so taking that mathematical-based definition and mapping it to what we've now co-opted it in technology, idempotency is the characteristic that ensures when running an operation over and over and given the same input, which directly maps to when multiplied by itself, that the same output is achieved every single time, so unchanged. So when we apply idempotency or think about idempotency in the context of web requests, of sending events, of doing web calls or invoking events, we want to make sure that no matter how many times that request has been invoked or called, with the same input, that we get the same effect outward. So idempotency, now you know what that means and where it actually comes from. So at this point, you're probably like, that's great, Adrienne. What does idempotency have to do with good serverless architecture? And I'm going to be one of those people that answers a question with another question. It says, well, have you heard about the 7 design principles of well-architected applications? Who here has actually heard of the 7 design principles of well-architected applications? Wonderful, you'll learn something here today. So these are not mine, these are borrowed from AWS. AWS writes these guides on what well-architected applications are, and they have these kinds of things, principles, best practices, and specifically the ones I'm going to share with you are looking through what they call a serverless lens. So that's a very specific context with which these principles apply. And very quickly, we'll go over them. The 7 of those are that they're speedy, simple, singular. So following the single responsibility principle, right? You're doing one thing at a time. And in the case of, say, functions, which is most synonymous with serverless, when people think of serverless, you do one thing at a time and only one thing in that function. You share nothing. So in this, when you choose to build serverless applications, usually you think of it in a stateless fashion. Because when, let's say, again, functions are the most common example, you're usually running that brand new execution every single time. So you don't want any kind of state that would have to be shared, because in order to take advantage of being able to fan out all of that work and make use of all of that hardware, you need to make it as agnostic as possible and not rely on any sort of state. That's not to say you can't do it, but we'll get into it next. So that's what share nothing means, that it assumes it's stateless. You assume no hardware affinity. So you've chosen serverless for a reason. You don't want to deal with the hardware. You don't care about it. Therefore, if you choose serverless applications, you will want to avoid using any configurations that depend on hardware, so CPU flags and things of that nature. You want to use events to trigger transactions. So this is where we start to encourage being more comfortable with asynchronous events and understanding that not everything has to be waited on by the person using it. We want to get more comfortable with sending out events and doing parallel work rather than waiting for everything to occur and happen and end all while the user is waiting. You want to think concurrent requests, not total requests. So a lot of the times when you start seeing these pricing tables and you see these are the number of requests that you get, you try to start optimizing, well, how could we lower the number of requests? How do we get fewer requests? And that's really not what we should be thinking about. We should be thinking about how many concurrent requests we can do at that time, because again, if you're able to make it as agnostic as possible and take advantage of all of the horizontal scaling that you are applying to your serverless functions or your serverless applications, then you're actually making use and taking benefits with serverless. You'll want to orchestrate your application with state machines, not functions. So again, when we start building more complex serverless applications, a common smell that you see is you start invoking functions from other functions, and that's never something that you want to do. If it ever gets that complex, you'll want to use something that is actually built for that, something like AWS step functions or Azure's durable functions, which is a library that provides the state management for you and a way to deterministically orchestrate your functions. And finally, the last design principle is designing for failures and duplicates. So that one is pretty self-explanatory, but I want to call it out because out of all of the 7 design principles that are here, this is the most important. Why is this the most important? Because this is the one that is impossible to do without idempotency. So it's very peculiar that they dedicate a whole principle to both failures and duplicates, right? Why not just say failures, or why not have 2, design for failures and design to incorporate duplicates? But that's because these 2 go hand in hand. When you think about it, failures almost always lead to retries. And if you think about it, how many times have we told people, turn it on and off again, rerun the code, resend the event, re-invoke it? A lot of the really, really weird edge cases that we get, or the very transient bugs that we can't seem to figure out, they almost always can benefit from at least trying it again. And so understanding that this is an effective solution, that just running it over and over or retrying it, we know that this is an effective solution because there are a lot of SDKs that have actually been building it in. There's retry functionality that's being built in. And so knowing this fact, knowing that failures are always going to occur, Werner Vogel said it himself from AWS, and knowing that retries are going to be a common possible solution to a failure, then we know that implementing those retries means that duplicates can and will occur. duplicates can and will occur. So if we're retrying something, anything, we're sending a message, we're retrying our code, we're reinvoking an event, that means we are explicitly telling our code to do something again. We are introducing those duplicates into our system. And even if you want to be a little pedantic about it and say, well, if we're using the automatic retry behavior, it's not me, it's the server or wherever it's being hosted, that's what's calling it again. We are introducing it by using that library or using that functionality. So if we're going to retry, we're going to have duplicates. And those duplicates come out because we are introducing those duplicates. So understanding that, we know that if duplicates exist, then idempotency is key to mitigate side effects. So side effects, what kind of side effects could those possibly be? Well, let's think about what happens without idempotency. So as I mentioned, I was with my husband on our way home from a road trip, and as we got to talking, I started to get a little bit hungry. And if there's anything you know about me, if there's anything you know about Adrienne, it's I love desserts. So if anybody has dessert recommendations, please come see me. I would very much appreciate it. So on the way home, I'm based in Las Vegas. We have a very popular dessert shop called Fried's. And as we're going home, I'm like, you know what, I'm gonna place an order so that we can have some cake when we get home, because why not? Browsing, looking through, who am I kidding? I'm gonna pick the world famous strawberry shortcake, because that's the best one. Place my order, and I am a happy Adrienne. Now we just have to get home. And through this road trip, we see that we're going through and we place this order. And when we think about what's happening now behind the scenes, now that this order has been placed, let's start with some layout here. We have me, Adrienne, the client here, who is placing the order. We have Fried's website, and for the sake of simplicity, let's say they have an API that is handling this. They might have some microservices architecture, maybe it places the order, maybe it starts an invoice, but we don't need to think about that at the moment. And from top down is the movement of time. So as we go further in time, that's how this diagram is meant to be understood. So I've placed the order, right? I'm ordering my cake, I'm ordering that world famous strawberry shortcake. The order has been placed. But it's at this exact moment that we actually enter the tunnel. And when we enter the tunnel, I lose network failure for a period of time. There's no signal. And at this time, I'm like, okay, I think the order has gone through. I have no idea because I'm in the tunnel. What I don't know is that the order is actually processed while I'm in the tunnel. And while I exit the tunnel, presumably what I would see if Fried's website is proper and handles these types of errors, I would regain my Wi-Fi or regain my signal, and I would see that error, right? I would see something like the order has not gone through, or I actually see something worse. I see a socket error that it says it didn't connect. I would see something that indicates that my order was not processed. And me, being the cake addict that I am, I'm like, well, I'm gonna get my cake, so I'm gonna place the order again. So I go ahead and see the error, and I resubmit my order. And when I resubmit my order, I get some more cake. I place that order, the order's processed, and great, there's cake that's on the way, I'm happy, I get a notification that says it's actually been processed and I'm about to get cake when I get home. But wait 1 second, if we zoom out on this timeline a bit, remember that request, the one that actually got processed while we were in the tunnel, that actually went through. Fried's actually processed that request. Fried made that order, they got that cake. There's a surprise cake coming on the way to me. So I'm gonna get 2 cakes, not 1. And a lot of people might agree that that's not necessarily a problem, right? Who's gonna complain about getting 2 cakes? But think about this in the context of other actual applications. What if your client gets charged twice? What if your bank account got withdrawn twice? What if any of these other items had happened more than the times that you want it to? That's the biggest point about idempotency, is that because there was no idempotency in the initial request or in any request for that matter, the intent of my request has not been captured. My intent was to order 1 cake, but at face value, Fried's or the API that Fried's is using can't possibly know that my intent was not to order 2 cakes? It got 2 requests. They were both valid. They were valid requests because there's no idempotency in place. And so it has to take it at face value that the intent was these are 2 valid, possibly separate requests. And that is the biggest side effect of having no idempotency built into these kinds of requests, that duplicate requests are considered valid requests. And really, that's a pretty harmful side effect, and I've explained to you why. Other than having too much cake, you get charged twice, the intent is not captured, and that's the most important part. And when the intent is not captured, it's going to run it as if that is a valid request. So how do we actually apply idempotency then? If we know how problematic this is, if we want to ensure that no matter how many times this has been run, we only get 1 cake, how do we do that? Well, there is the most generalized way of understanding idempotency, and there's 3 parts to it. The first is an idempotency key. So this is something that is usually generated by the caller. In this case, it would be the client, the website, or the request that I've sent from my phone. And this is something that is a unique identifier. This is something that says, this is the very specific request of Adrienne Tacke ordering a world-famous strawberry shortcake at this particular time. And we are able to understand that intent, that request on its own through this key. Another part is an idempotency layer. So this acts like a filter, and this is what decides what to do with the requests. So in the context of a web application, that could be a cache, that could be some sort of other database persistent layer, really, or this could be some of the, I apologize, not the database layer, that's the next layer. The idempotency layer could be some business logic that is on the API that says, check this unique key against something. And that something is the persistent storage, which is the third piece of idempotency. So this is what stores the state. This is the source of truth for our application, for our idempotency keys. And in some cases, you can even use it as a list of checkpoints in your retry behavior. So with all 3 of these pieces, we can actually implement idempotency in our application. And let's see how we do that. So we're back again. This is my phone. I'm about to order. And we want to first generate a unique identifier, right? So in this case, let's say we just generate some UUID. This could be a place order event. And once I've placed my order, we actually send that idempotency key as part of my request. So we've placed that order, it's invoking an event order, a place order event, goes to the API. This time, in a persistent store that we have, we're going to now, instead of immediately processing the request, we'll say, hey, can you get this idempotency key that I've sent in this event? And if there's nothing found, then we can safely assume that this process has not been started yet, that this particular request has not been seen before. And so we run whatever handler that is. We run what was processing the cake, maybe it runs the invoice, whatever. We can safely say, Freeds, go make this cake. And once that has happened, we then now save that state, right? We set the idempotency key as well as the result of what happens there, even if it's an error or if it's just been a successful process of a cake. And now that's what our initial request looks like with idempotency built in. And this is important because let's say that same workflow happened before, that same error happened when I exited the tunnel and there was no response received by the client. Well, now every subsequent request that is going to happen, let's say it goes through again, whether it's me placing it or whether it's the auto retry behavior that's been placed in, we'll place the order in the event, we'll get the idempotency key in the event, so we'll check our persistent store, and it's going to say, hey, this actually exists. So instead of rerunning it, we're just going to return the actual result that has been seen. And we send the response to the client. And no matter how many times this has been run or is continuing to run, this same workflow is going to occur because we have these idempotency keys staved in our state as well as the result. Now, one question that I got from the last time I gave this talk was, well, isn't that persistent store going to get extremely large? Yes, it will if you don't delete it. And so there's something called similar to time to TTL indexes, time to expire indexes. So you can set a specified amount of time for how long these keys are actually kept in that storage. For the most part, you don't need to keep it forever, right? You want to have it so that it exists when it checks against the filter if it's been processed before and can understand whether it's a duplicate request or not. So the default for that usually is keeping it maybe an hour. And then that way you start to offload all of the old requests and don't have a really gigantic persistent store of idempotency keys that you don't need anymore. And so now that we've seen one way to implement idempotency, let's take a look at some of the libraries and tools that are actually either having it built in or are encouraging it in their systems. So the one I'll really focus on today is one that's actually from AWS Labs. This is AWS Lambda Power Tools, which they have an SDK for Java and Python. So pretty much everything that I told you is built in here. So they have an idempotency key, which they do a hash representation of the entire event or a specific configured subset of that event. So depending on if you need that entire event information to generate this uniqueness or not, you can set that yourself in the idempotency key. And of course, the persistent storage layer that it uses is DynamoDB, because that's the only one that's supported for now because AWS, right? So as an example, you can see here that this is the Python example here. And we have our handler, we have our persistence layer that we declare, and this is where we can return our, what is it doing here? This is the create subscription payment. So here, in this case, we use the product ID, and we also import the, this is what I wanted to talk about, the idempotent status here. Some of the features of this particular lab is that it prevents multiple Lambda handler function executions on the same payload during a time window. So it actually does that for you automatically, and you can set the time window that you'd like it to look through. It will ensure that the Lambda handler returns the same result when the same payload is called. So again, using that particular idempotency key, it will automatically do what we showed you in the request that was idempotent, which is if it already has a result and it sees that same unique identifier, it will just send you back the same result. It reuses the same DynamoDB table to store idempotency state. So this is very helpful because it adds the function name in addition to the idempotency key as a hash key. So this is very similar to Azure Durable Functions, where when it does the retry behavior again, let's say it fails in the middle of that orchestration, you can go back to this table and just replay every single step that has occurred. And that's another reason why idempotency is important, because if it's going to replay this in the event of a failure, you want to make sure every piece of that replay is deterministic, is idempotent. It has no side effects, no matter how many times that it is run. And finally, you set expiration period for idempotency records. So again, with DynamoDB, you can set how long to keep those records so that it doesn't blow up and become this huge persistent store. So there are some other really great tools and libraries here. One I'll mention is the Stripe API. So they've kind of been setting the standard when it comes to web requests for idempotent requests and implementing idempotency keys. And if you check out their blog about how to implement idempotent requests and idempotency, they talk about how they built this into their API. And a lot of other APIs follow their lead when it comes to how to implement idempotency keys. There's also idempotent API, which performs additional idempotency checks, which is a NuGet package. So for anyone that is in the Microsoft LAN or C# LAN, this is one really good similar thing that you can check out. There is a blog post by .NET Nakama that explains why this can help for fault-tolerant web APIs. We have step functions, of course, which is AWS's serverless orchestration service. And we have durable functions, which is the Azure equivalent of the orchestration service. And then, of course, we also have some Cisco APIs that have idempotent post, delete, or put requests. So a couple examples are Intersight and the Meraki API that we have specifically for the Meraki dashboard. So depending on which request that you're running, they have implemented it to be idempotent and built in by default. And with that, I want to say, Hvala lijepa, Infobip Shift. I hope you learned something about idempotency, even at the least to pronounce it. But if you have any questions, I'd be happy to answer them. Come up or raise your hand, and then that's all my information. So thank you.
Any questions? Yeah, one in the back, and microphone on its way.
So just a short question. Wouldn't it be better to push the checking of idempotency of the key, right, down to the persistent storage layer? Because if you have multiple instances of API, you can get into concurrency issues, where when you check for the key, another instance already pushed another key with the same payload inside. So one would think that there are no orders, and there would be 2 orders in the end. So wouldn't it be better just to do it in the storage levels?
It depends. So there are very weird use cases where it would be better to do both a check as well as a database lock on the particular transaction of checking the ID. So those are those use cases. I would argue that when you have them spread out, that there should still be a single point that acts as the filter. So it depends. So yes, you can do it. And if you are distributed, then there are some use cases where that would be in play. But so this is not an end-all be-all, like it only ever exists on the API layer. There are cases where they would happen as well at the database layer or the persistent storage layer.
We have another question right here. We need a mic for you.
Oh.
It's on its way.
Sorry. So since you said that, if I remember correctly, you said that even in the case of errors, you would save result and return the result from the function. Is it correctly?
Was your question, is it proper to save the error
No,
in there?
if I remember correctly, you said when we call the functions, even in the case of the error in the function, we would return on the next occasions of calling that function the same error, right?
Yes.
Same as if it is a normal result, right?
Correct, yes.
Then how do you handle the situation when you resolve the error which occurs on the other side, on the persistent storage or wherever the function, whatever the function does? If you resolve in the meantime, you cannot test with the same input parameters. You would get error even if the baseline error would be solved.
Okay, if I think I understand your question correctly, let's say the first flow of the request results in an error, and let's say we save that error in the persistent store. The reason to do that is, let's say a duplicate request comes in, you can automatically skip the running of it because it already has saved that error. Now, if it has shifted outside of the time window of checking duplicate requests, and this has now become a valid request, and it does actually return a proper result, then that's still important to save in that persistent layer so that any other subsequent requests can check against it and see that this has processed normally. In the event of handling the errors, that is on the job of the client to understand what is happening. So there's been a lot of talk about what do you do when you send a request, it's actually processing, and another request comes in at the same time. Is that an error? Is that a try again later? Is that it's processing? So that's up to debate. It depends on your application and depends on what you think is correct. I personally like sending the most accurate description, which is having a status code that says there's an existing request that's already in place. And so sending that back to the client and telling the client that it is being processed at this time. So hopefully I understood your question. If not, please come up and we can talk about it more.
Anyone else? All right, Adrienne, thank you so much.
Thank you.